The quantum algorithm finds a solution and solves a given task within an appropriate time, and you use it with a high-level programming language for the AI model or with the intermediate data structure. And you also structure the domain by using quantum logic, and you use the state of superposition to process ambiguous elements. And these ambiguous elements are part of the input text. You assign them to the levels of the multidimensional reasoning net by using a ternary quantum gate. And you also process them by using binary or ternary gates. For example, a word can be a noun or an adjective at the same time. And by measuring, you convert the state of superposition of quantum bits into a classical state. During the superposition, the state of the qubit is 1 or 0 at the same time, and after the measuring, it is 1 or 0. The result of the measuring depends on the amplitudes alpha and beta. If a qubit in the state alpha 0 and beta 1 is measured, it is in the state 0 with a certain probability and 1 with another. Quantum algorithms consist of inputs and outputs, gates and wires. The algorithm uses oracles. Oracles are circuits which define the property of a function. Circuits transform the state of an input. While classical circuits are reversible, quantum circuits are one-directional and they move from left to right. At the end of the circuit, you measure the states of the qubits. And quantum circuits consist of 3 elements. They consist of the gates, the registers, and the wires. And the registers contain qubits. The gates perform logical operations on the input, and they transform the state of an input. The NOT gate is the classical counterpart of the Pauli gate, and it negates the input. The Toffoli gate inverts the value of the third of 3 qubits if the first and the second qubit are 1. And for the reasoning net, you use the Toffoli gate also in its ternary form. The Hadamard gate, or H gate, does not have a classical counterpart, and it effects the superposition of x. If the input is 0, the output is the sum, and if the input is 1, the output is the difference. The wires carry the signal between the gates and the registers, and they are electrically conducting. Quantum effects influence the transport properties, and the algorithm initializes the state of the qubits. It applies a quantum wire for n qubits. It puts the register x into superposition and performs multiple iterations of the oracle. And f of x equals 1 if x is a solution and otherwise it is 0. The Hadamard gate is a single qubit gate and it effects the superposition of x. Quantum-controlled phase flip does not change the state of 0. And if it's reasonable, you apply the gate multiple times. The logic of this quantum circuit and quantum algorithm is useful for the high-level programming language. You simulate it with a reasoning net by using quantum logic to describe and process the domain task.